Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Optical Spectroscopy from the paper Physics at Nanoscale. So the learning objectives of this module are: first, we will discuss the various optical characterization methods. Second, the photoluminescence setup. Third, the energy levels in nanoparticles will be discussed. Next, we will discuss about the absorption spectrometry. Then we will discuss some of the spectroscopic techniques: ellipsometry, fluorescence, phosphorescence, etc. So students, let us start with a basic introduction about the module. The term spectroscopy was first coined in 1666 when Sir Isaac Newton demonstrated the dispersal of white light through a prism into different colors. Contemporaries thought they were looking at ghosts and called themselves ghost watchers. Ghost in Latin in the spectrum, while watcher in Greek is scopus, hence the term spectroscopy. Spectroscopy is basically the measurement of the interaction of light with various materials. So by analyzing the amount of light absorbed or emitted by the sample, we can determine what it is made of and how much of it there is. Optical characterization methods. So students, as shown in this figure, if we have the excitation photons striking a sample, then it can undergo four kinds of phenomena. First, it can get Rayleigh scattering, Raman scattering, it can undergo transmission, and lastly, we can have a photoluminescence. So let us have a short or a brief glance on all these phenomena. First is transmission, that is untouched photons. Second, photoluminescence, which includes fluorescence emission within 10 to the power minus 5 seconds and phosphorescence emission after 10 to the power minus 5 seconds. So the emission wavelength usually longer than the excitation wavelength, Stokes shift. Now next is the Raman scattering, which is the inelastic scattering in semiconductors. It can be phonon-phonon scattering. Next is the Rayleigh scattering, that is, it is the elastic scattering and there is no change in the wavelength. So students, this table summarizes the different techniques, the synopsis, and they are used in solid state physics. First is absorption spectroscopy. So it scans the wavelength, measuring the intensity of transmission. It is used in optical absorption, band gap, energy level spacing determination. Next is photoluminescence. Now here there is a fixed wavelength of the laser and it scans the output wavelength. It is used in optical recombination transitions. Next is photoluminescence excitation, PLE. So here we are fixing the wavelength and we scans the lambda. So tunable laser or monochromator is used. It is sensitive to transitions that pumps the optical emission. Next we have the Raman scattering, where the laser in is scanned, that is lambda out very close to lambda in. Stokes, anti-Stokes peaks, they provide information about the phonon energies. So this is the schematic showing how the PL of the bulk semiconductor usually have peak at the band gap, while the absorption and photoluminescence emission is broad and can determine the density of states. So this is showing the exchange between the energy levels occurring, that is in the molecules, absorption and photoluminescence emission peaks are coupled of S1 and S2, which are shown over here, with the vibrational energy, while PL peaks are the couple of S0 and vibrational energy. So this is the schematic showing a photoluminescence setup. Now we have this optical setup consisting of the entrance slit, which is f by 4, the collimating mirror and a focusing mirror. So this entrance slit is connected through a fiber optics to the XYZ stage. Now here the whole setup is placed on the spectrometer SP150 having f equal to 150 mm, f by 4 dual grating turrets. Now this light falls on the two lenses, f equal to 127 mm, the first one, and the second one is f equal to 63.5 mm, which falls on the sample which is placed in a cryostat. So using the optical spectroscopic methods, we can measure the different energy levels in semiconductors. In the case of semiconductors or in the nanoparticles basically. So here in this figure on the left hand side, it shows a cadmium, the first part A shows a cadmium selenide bulk semiconductor having a valence band and conduction band. And now if we'll make a quantum dot of it, that is the cadmium selenide quantum dot, then the energy gap between the energy levels increases as shown in this figure, and the energy gap for a quantum dot equal to Eg naught plus h cut square pi square by 2 MEH multiplied by R square, where MEH equal to Me multiplied by Mh divided by Me plus Mh, where Me is the effective electron mass and Mh is the effective hole mass. The last figure over here shows the absorption spectra of the cadmium selenide quantum dots. So PL and PLE peaks in cadmium selenide quantum dots can be used to compute energy spacing and the relaxation characteristics for electrons and holes. Now the figures on the right hand side, that is the first figure on the left, shows the evolution of UV visible and PL spectra of the core shell nanocrystals upon the growth of the cadmium selenide shell in a typical reaction. And on the right, it shows the asymmetric PL of core shell nanocrystals with 5 monolayers of cadmium selenide shell. So ordinary light excites all color quantum dots. So as you can see over here, any light source bluer than the dot of interest works. So here a quantum dot changes the color with size because additional energy is required to confine the semiconductor excitation to a smaller volume. So these are the PL spectra for the zinc selenide, cadmium selenide and cadmium telluride nanoparticles. Now here the material band gap determines the emission range. Particle size tunes the emission within the range. Nanocrystals quantum yields are as high as 80%. So, narrow symmetric emission spectra minimizes the overlap of adjacent colors. So, let us now discuss another optical spectroscopy, that is absorption spectrometry. So the first figure shows a single beam instrument and below that we have a double beam instrument. So here both the setups, they have a filter or a monochromator for wavelength selection, a transducer and a readout device for data collection. Double beam instrument splits the excitation source for faster acquisition and greater accuracy. So our UV visible system is a single beam instrument with a monochromator. So now the measurement principle of this spectroscopy is that for a single beam instrument, data is acquired twice, once with a reference cell and once with a sample cell in place. Signal rotation is taken to give the absorbance. For a double beam instrument, adjust 0 with the shutter closed. When the shutter opens, the absorbance is read directly from the difference amplifier. Now the application is to characterize the optical absorption. Advantage: relatively simple instrument. Disadvantage: limited sensitivity, especially when the change in absorption is small compared to transmission. So students, let us now discuss about the photoluminescence and photoluminescence excitation, PLE. Let us first discuss about its setup, which is shown in this figure. Now a combined PL and PLE system has two monochromators for wavelength selection of excitation and emission. So a single PL system can have a laser as an excitation source. A tunable laser can also be used instead of the excitation monochromator. Now here a beam splitter and a reference detector is used to compensate for the variation in excitation intensity. Let us now discuss the measurement principle. PL excitation wavelength is fixed. Emission intensity versus wavelength is obtained by scanning a monochromator of spectrometer. Now in the case of photoluminescence excitation PLE, emission is detected at a fixed wavelength while excitation wavelength is scanned by a monochromator or a tunable laser to obtain the emission intensity versus excitation wavelength. Let us now discuss the various applications of PL and PLE. This provides both optical absorption and emission information. Its advantages are: PLE is similar to absorption in some sense with much better sensitivity. Detection limits can be 3 orders of magnitude smaller than those encountered in absorption spectroscopy. So let us now discuss the another spectroscopic technique, that is spectroscopic ellipsometry. Ellipsometry is generally a non-invasive, non-destructive measurement technique to obtain the optical properties of a sample material by means of the reflected light waves. Here the technique measures a relative change in the polarization and is therefore not dependent on absolute intensity as long as the absolute intensity is sufficient. This makes ellipsometric measurement very precise and reproducible. Now the basic principle in ellipsometry is shown in this figure, where a monochromatic plane light wave is directed at the surface at oblique incidence. The plane of incidence is defined as the plane perpendicular to the surface and containing the vector which points in the direction of propagation of the light wave. This vector is called as the vector K incident, and perpendicular to K incident are the two mutually perpendicular vectors for the electric field E vector and magnetic field B vector of the light wave. So the E vector composed of two components which are mutually perpendicular and to K in. The two components of E vector are respectively parallel and perpendicular to the plane of incidence as shown in this figure. Now here the vectors are named from their German names parallel and senkrecht, and are from this given the corresponding Greek letters pi and sigma respectively. Now here the incident light wave is linearly polarized. Polarization will be it can be pi and sigma component of E can be seen as oscillating with an amplitude and mutual phase, causing the endpoint of E to move in a straight line in the plane of pi and sigma components. So this figure shows the basic idea of the ellipsometry technique. Ellipsometry is a sensitive optical technique, as we have discussed before, for determining the properties of surfaces and thin films. If a linearly polarized light of a known orientation is reflected at oblique incidence from a surface, then the reflected light is elliptically polarized. The shape and the orientation of the ellipse depends on the angle of incidence, the direction of the polarization of the incident light, and the reflection properties of the surface. So modeling the data gives us the film thickness. So students, let us now discuss the types of ellipsometry. So the types of ellipsometry are: first, null ellipsometry; second, photometric ellipsometry, which can be a phase modulated ellipsometer; third is spectroscopic ellipsometry. So let us now discuss the null ellipsometry. Here we choose our polarizer orientation such that the relative phase shift from the reflection is just cancelled by the phase shift from the retarder. So as you can see, which is clearly shown in this figure, and we seek rho is equal to imaginary of Rp by Rs. We know that the relative phase shifts have cancelled if we can null the signal with the analyzer. Next is the phase modulated ellipsometer. So here students, we are not using any kind of retarder and we seek rho equal to imaginary of Rp by Rs. So using a polarizer birefringent modulator, the source light is incident on the sample and then through the analyzer it is collected through a photomultiplier tube. Let us now discuss the applications of optical spectroscopies. First, they are used in research, that is to determine in the case of thin films, surface structures. Emphasis is on accuracy and precision. So in the case of spectroscopic, we can analyze multiple layers, determines the optical constant dispersion relationship, where we can also examine the degree of crystallinity of annealed amorphous silicon. Next, we can also use in semiconductor applications, that is in the case of solid surfaces, industrial applications in fabrication. Emphasis is on reliability, speed and maintenance. It usually employs multiple methods. So let us discuss the another optical spectroscopy technique, that is fluorescence. The absorption of energy from a radioactive source by the atoms can result in the atoms in an excited electron level. Atomic fluorescence occurs when the excited atoms emit radiation after initially being excited by the absorption of photons. Atomic fluorescence is the optical emission from gas phase atoms that have been excited to higher energy levels by absorption of electromagnetic radiation. So the main advantage of fluorescence detection compared to absorption measurements is the greater sensitivity achievable, because the fluorescence signal has a very low background. The resonant excitation provides selective excitation of the analyte to avoid interferences. So atomic fluorescence is useful to study the electronic structure of atoms and to make quantitative measurements. Analytical applications include flames and plasma diagnostics and enhanced sensitivity in atomic analysis. So because of the differences in the nature of the energy level structure between the atoms and the molecules, the laser-induced fluorescence from molecules, it is very crucial to discuss. So let us now discuss types of fluorescence. First is resonant fluorescence. Occurs when the fluorescent radiation is of the same wavelength as the absorbed radiation. Resonant fluorescence is the type that is used most often for quantitative analysis. Next is direct line fluorescence. It occurs when an electron in an excited state emits radiation upon falling to an electron level that is above the level from which the electron originally absorbed radiation. So the wavelength of the emitted radiation is longer than the wavelength of the absorbed radiation. Next is stepwise fluorescence. It is preceded by absorption and collision, deactivation to a lower excited electron level. Fluorescence occurs when the atoms emit a photon as the electron or by collision deactivation. So let us now discuss types of fluorescence. First is resonant fluorescence. Occurs when the fluorescent radiation is of the same wavelength as the absorbed radiation. Resonant fluorescence is the type that is used most often for quantitative analysis. Next is direct line fluorescence. It occurs when an electron in an excited state emits radiation upon falling to an electron level that is above the level from which the electron originally absorbed radiation. So the wavelength of the emitted radiation is longer than the wavelength of the absorbed radiation. Next is stepwise fluorescence. It is preceded by absorption and collision, deactivation to a lower excited electron level. Fluorescence occurs when the atoms emit a photon as the electron or by collision deactivation. Now let us discuss the phosphorescence. Excitation during both fluorescence and phosphorescence occurs when radiation is absorbed by an electron in the ground state of a molecule, causing the electron to be excited to a higher electron state. So during the absorption of the electron, it does not reverses its spin. Generally, excitation occurs from a singlet ground state to an excited singlet state. So the transitions between the excited singlet state and the ground state, the excited triplet state, or between the triplet excited state and ground singlet state are the examples of inter-system crossing. So the considerable barrier to spin reversal that exists in a molecule prevents the inter-system crossing from occurring as rapidly as singlet transitions. Because of that barrier, phosphorescence occurs on a much longer time scale than fluorescence. So students, let us summarize what we have learnt in this module. Firstly, we discussed the different optical characterization methods. Secondly, the photoluminescence setup, its schematic and its measurement principle were discussed. Thirdly, the various energy levels in nanoparticles were discussed. Next, we discussed about the absorption spectrometry. Lastly, we discussed about the various spectroscopic techniques, ellipsometry, fluorescence, phosphorescence, etc. Thank you.